Okay, good morning, ladies and gentlemen. Thank you, Mr. Chairman. My name is Sylwester Samborski. I came from Poland, and my presentation will be on damage identification in FRP composites based on elastic wave analysis. Actually, this is about acoustic emission and other issues that we use during our delamination experiments. My collaborators are Jakub, Jakub Skoczylas, Jakub and Izabela Korzec, my PhD. Two of them are already doctors. So, shall I switch with a space maybe? How do I move forward? The arrows? Now it works, yes. So this is the outline. Motivation basic on fracture mechanics, elastic couplings in composite laminates, finite element modeling of delamination, acoustic emission aided experiments, and in the end, summary and conclusions. So my motivation is that we had a grant which was acknowledged in the first slide for testing for fracture delamination of coupled composites. Those composites are untypical because, for example, if you try to bend a beam made of such a composite, it tries to twist, so it is not classical symmetrical laminate. There is some basics of fracture mechanics, classical fracture modes, opening, shearing modes, and anti-plane shearing mode also, mode 3, and the respective standards according to the ASTM. I was concentrated with my team on DCB and ENF especially. Now we are doing some ECT experiments, the third one, which are not standardized. And at the moment, we are cooperating with the University of Pisa, with Paolo Valvo and Daniele Fanteria. This is some basics of couplings. We have some forces. N are the forces in the laminates, normal forces. M are the moments. Q is the local stiffness matrix. Z is the dimension starting from the zero layer to each ply, as you can see in the drawing. And also epsilons are the strains and kappas are the curvatures. So in the block matrix form, you can present this as follows. A is the extensional stiffness matrix, D is the bending stiffness and coupling matrix, and B is in-out of plane coupling matrix, which is the most important here. And this is another presentation of the same in another form with some more details. You can calculate any term of A, B, and D matrix with respect to Z dimension, as I said, localizing the ply. So usually the A and D matrices can be either fully zero or fully coupled. And concerning the in-out coupling matrix B, there are several cases. From uncoupled to extension bending, shear twisting, and here, for example, extension bending, also extension bending, extension twisting, and shear bending, many possibilities. It was very nicely described by Christopher York in 2015. So I took that idea and a little bit developed. When you are speaking about the criteria for cracking, for delamination between the plies in a composite, in the typical finite element software, which is Abacus, you have three different criteria. First is power law, next is BK law, and the third one is the reader law. The third one is the most general. For that reason, we used that one. And you can easily imagine that if G2C equals G3C, it becomes the BK law. So in general, definition of this parameter GI, which is fracture toughness, it is another material constant, can be defined as follows in the first frame. But my question is, how about changes of G along the width of the specimen, or in other words, along the lamination front? So this is some details of the finite element model with application of the so-called virtual crack closure technique, which is somehow explained here in the bottom. It says that after you move back the cracked hinges, it's complete recovery of the energy, which is not physical, but it works well for simulations. So as you can see here, the mesh was densified around the red line, which is the initial crack front, which is flat. And then when we consider different couplings, you can see that the fronts are not linear, not flat. For example, the biggest drawing shows the typical situation for unidirectional specimens. And if we have some couplings, for example, bending twisting or bending extension, the shape of the front can be different. And the question is, can I use the ASTM standard to get the fracture toughness, or shall I do something else? So my idea was to introduce some additional parameters describing the discrepancy of the results I obtained compared to the unidirectional specimen. This is the real fracture surface, delaminated fracture surface, and the real delamination front in one of the experimental specimens. You can see it is not flat, not perpendicular to the x-axis. And this is another example of some simulations with different angles. BE means bending extension coupled specimen, or B model. 0, 5, 10, and so on. This is the angle of fiber orientations, which again can be seen here. You see this is theta, so you can modify this in the abacus model. And what we can see here, that even though in such a case with bending extension, the distribution of surface energy strain energy release rate is flat, it becomes more and more narrow. So you can describe this by some parameter. And for bending twisting specimens, so when you bend the specimen, it rotates automatically. There is also some skewness of the distribution. So you can observe later that the lamination starts from one edge of the specimen as it is presented here. You can see on those screens that coming in the B, in this part, from the very first step of the lamination propagation to the next one. When you go to the bottom, you can see that from one side, from right side of the specimen, the lamination propagates, so it's not symmetric. And also, what is strange, when you try to open the specimen, somehow there is also the antiplane shear, which is shown in the plot on the right, big peak of G3. To describe this, and basing on the abacus data, I tried to introduce and define some equipolant vector. Some basics of these definitions are here, and I had to use the Python scripting to to dig out the data which is encapsulated in standard files of abacus, which cannot be presented otherwise. You must use some special procedures. And after this definition, I obtained such results. So for ENF specimen not coupled, bending, twisting coupled, and bending extension coupled, the procedure turned out to work quite well, even though the front shape during propagation can change from convex to concave or rotate to one side. The definition of equipolant vector works well. Next, which is actually in the title of the presentation, I would like to tell you about some results of me and my PhDs about the acoustic emission applied to the experimental work. So, for example, for DCB opening specimen, we get such a curve like this in a navy color here. So there is a peak and there is some continuation of the saw-like line. And the most difficult question for the experimentator is, where is the beginning of fracture? So there are several ideas. For example, the maximum of the load, P max, the beginning of the nonlinearity, NL, 5% decrease of the stiffness. And our method is with acoustic emission, which is not, of course, we didn't invent this, but we try to test it, to apply this, and so on. And according to my experience, acoustic emission is very precise because, as you can see in the screen, there is a peak of energy or another parameter of acoustic emission, which shows you precisely the beginning of fracture, of propagation of the lamination. As you can see here on the left, top left, depending on the point that you accept as the beginning of fracture, you have different values of G1. And G1 is the key point is this experiments, because you want to decide what is the critical value after which the laminate will fail. And it is quite important because, as you may know, such laminates are used in airplanes, and this is the matter of safety. So in the next slide, you have also other experiments, very recent. Just yesterday, my students sent me that data. They at the moment they use two piezoelectric transducer also to measure additional parameters such as the velocity of crack when it is active. And in this screen, you can see, first of all, application of AE point, which is acoustic emission, and another point which is connected to the beginning of some nonlinearity. And you can also compare this with the photos of real crack tip. Green line here is one of the parameters of the acoustic emission signal, which is cumulative energy. And you can realize that when the energy plot starts to grow up, there is the beginning of fracture, and in the end, it has quite big value, even though the unit is quite small, picojoule. In the next two slides, you have another examples, and again, when, for example, cumulative hits start to grow, hits is just one event of acoustic emission. There is the beginning, and this is the value of the load, for example, 69 newtons that we take to calculate G1C. And in another plot, we can use cumulative energy. Again, when the energy starts to grow up, there is some force, for example, P equal 80. I must also say that classical parameters of acoustic emission are hits or events and counts. But at the moment, the producers of such equipment provide some software with Fourier transform or wavelet analysis for deeper recognition of the damage phenomena in the material, and you can see in the photo below there is some bridging effects of the fibers which are being pulled out from the matrix. And after you analyze the signal with, for example, with FFT, you can decide, is it matrix breaking, fiber breaking, or maybe fiber pull out. It depends on the frequency. For example, for breaking of fibers, it is 300 to 400 kilohertz. It also shows that the word acoustic emission is rather traditional, because in fact the frequencies are much below the hearing range of our ears. It's from 50 kilohertz up, even to 1 megahertz. This is some example of wavelet analysis. So you can see here on the left those colorful pictures where you can decide what frequency is dominating and what is accompanying. So you can realize that the fracture process is a complex process, not just delamination, but also fiber pull-out, fiber bridging, and so on. So everything happens at one moment, but keeping your eye on this map, contour map, you can decide what is the most important at the moment, at the specimen that you test at your experiment. There is also some data from Izabela Korzec, my PhD, which shows for another type of composite that any of the measure of acoustic emission, either heats, energy, or counts, gives similar conclusions that when the loading process ends, for example, here you can see brittle fracture, every parameter of acoustic emission reaches its highest value. And to sum up, I have shown you the results of acoustic emission aided study of delamination detection in composite with couplings. Advantages of using signal analysis tools to the raw AE signal have been discussed, and prospects for future research on coupled laminates have been revealed. Thank you for your attention, and here my contact data. Thank you very much.